Okay, we're continuing with horizontal projectile motion, and what I set up here is a second problem in which we know the height of the cliff. There's the cannon, there's my cannon, here's my cannonball over here getting fired. The cannonball, we know its initial velocity now. It's in the x direction initially, it's at 50 meters per second. The height is going to be 50 meters high, and what we don't know is how far it's going to go. So we want to calculate the range, and the range is going to be what I'm going to call my delta x over here. So that's my displacement in the x direction. This is my displacement here, delta y, in the y direction. Now, a lot of people confuse delta x and delta y, and what I see is people thinking that delta x is some kind of speed in the x direction. It's not. Delta x is simply a distance. It's a change in position. So in this case, the position's going one way, it's changing, it's just the distance or length that something's going to travel. It's measured in meters or whatever you measure length in. Same thing with delta y, except it's a change in position in the vertical direction. So last time we said that we know something about horizontal projectile motion, don't we? We know that the velocity in the x direction here, which I just put in yellow, doesn't change. So if I've got 50 meters per second here, when the ball is over here, I'm going to still have 50 meters per second in that direction. And when it finally hits the ground right there, I'm going to still have 50 meters per second in that direction. So the x component to the velocity, where this is my x direction, the x component never changes. So that's the easiest thing to see. You never change the value of the magnitude of the x component for these velocities. The y component, however, does change, and it changes because gravity is going to be a problem accelerating the ball or the object downward. So again, we want to find the range, and we want to think of two things here. We want to think of vertical motion, vertical, and I suggest that when you solve the problems, you split your homework sheets up horizontal, like I'm doing here, and do one at a time. Now, vertical motion, we know the formula, delta y is equal to the initial velocity in the y direction times time, plus 1/2 acceleration in the y direction times squared. What is my change in position in the y, or vertical direction? From start up here where it starts to where it finishes, the ball actually drops downward 50 meters. So my change in my vertical position is minus 50 because it's going down 50. The initial velocity in the y direction is 0. Because when the ball is fired from the cannon, it's going horizontally. It's not going up or down. So this initial velocity is 0 times time plus 1/2. The acceleration in the y direction is going to be what? It's going to be negative 9.8 t squared. So we're going to solve this formula. Negative 50, 0 times anything is 0. That's going to be negative 4.9. Where did you get the 4.9 from? 1/2 of 9.8 is 4.9, and it's negative 9.8 there, times t squared. So my time then, when I solve this, is going to be the square root of 50 over 4.9, and that's going to be in seconds. Now on the horizontal end, we know that delta x is the same type of thing. The initial velocity in the x direction times time, plus 1/2 acceleration in the x direction times squared. However, there is no acceleration in the x direction because we just said that in the x direction, the x component to the velocity never changes. You don't change velocity, then you have no acceleration. Acceleration is 0, that term goes away, and this formula just reduces to delta x equals the initial velocity times the time. So we don't know what the initial, we don't know what this displacement is. That's the range. That's what we're trying to find out. All right, delta x is how far the cannonball went in the x direction, what its range was. The Vx, velocity in the x, we know is 50. That's what we started with, and that's what it continues. The time, though, is whatever this value is here. We're going to plug in for time, and we're going to plug this in here, whatever this number was, 50 over 4.9. And I'm not solving these now just to save some time in doing this. Take me some time to do it on a calculator, but I think you get the idea. And this is going to be in meters then. So this here is going to be the range. Okay? And we'll do another problem in the next video.